Okay, so lesson 3.7 is all about differentials, which is what we've been doing. We've done derivatives. It's just going to be written a little bit of a different way, not much change from what we've been doing. So this should be a good review. Don't forget that to get the equation of a tangent line, you need preferably a point and a slope. Sometimes this point could be the y-intercept specifically, but you don't have to have the y-intercept, so just any point and the slope are going to get you that line. Okay, one thing that I will point out, so we've talked about this form, this is point-slope form of an equation. The book uses this formula in this lesson. This is the exact same thing as this. It's just written a little bit differently, so let me tell you why. So this f of c, that is y1. And they said y equals that. Well, what they did was they added y1 to both sides. So if I added y1 over here, this would be y1 plus m times x minus x1. So it's the same thing here. So y1 plus f prime of c. Remember, the derivative is my slope of the tangent line. So that is m. And then my c value in this case is x1. So if that's true, if all of those things are true, this is the exact same thing as this, except with y1 added over there. So it really is the same equation. Don't let weird forms confuse you. You're still doing the same thing. All right, so example 1 says find the tangent line approximation. So this is a little bit different. When they say find an approximation, we're going to have a little bit of an error. And so we're going to talk about that. But they gave me an equation of the function, and they gave me a point to find it at. So the first thing I'm going to do is just find the equation. So I'm going to find the slope, and then I'm going to use this point to help me out with that. So the slope is the derivative. So the derivative, f prime of x, is 3x squared. The derivative of x cubed is 3x squared. And they want me to find that at this point. Well, this is my x and this is my y. My derivative only has an x in it, so I'm just going to place that 2 right there. So f prime of 2 is 3 times 2 squared, which is 12, because that's 3 times 4, right? So that means my slope is 12, the slope of my tangent line. Okay, so then I'm going to write my equation. So y minus my y value equals m, which I just found was 12, and then x minus my x value. And then I am going to simplify this a little bit. I think I'm going to put it in slope-intercept form just because it'll make things easier in the long run. So y minus 8 equals, this would be 12x minus 24. And then I'm going to add 8 to both sides. So that would give me minus 16. Okay, so here's my equation of my tangent line. And here's what they're wanting me to do. They want me to come up with an approximation, and then they want me to compare some things here. So I'm going to compare. All right, so the first thing they want me to compare is my actual function compared to my tangent line approximation. So what I'm going to do, so they were talking about the point 2. We talked about that before, where we say, okay, well, if I'm going to find this open interval containing x equals 2, I'm going to look all around it. So I'm going to look at like 1.9, and then I'm going to get a little bit closer to it and say, how about 1.99? I could have even done another one in there and said 1.999. I really only need a couple, so I'm just going to do that. And then after 2, that would be 2.01. And then back here, I'm going to put 2.1. So I'm getting further and further away from it. Okay. So here's what I'm going to do. I'm going to take my x values, my 1.9, and I'm going to plug them in. So this was my original function. This is my tangent line approximation. So I'm just comparing those two things. That's what they wanted me to do. Compare the y values of the linear function on the open interval. Okay, so let's start with this one, 1.9. If I put that in there, 1.9 cubed. So 1.9 to the third power is 6.859. And then if I put it in here, 1.9 times 12 minus 16 is 6.8. So what you'll notice is this is pretty close, right? It's only 5/100ths away. And then 1.99 cubed, not to the second, to the third, is about, so I'm going to round this. I'm going to say that's about 7.881. And then if I do 1.99 times 12 minus 16, I'm getting 7.88. So again, it's just a little bit off, but look at the difference here. So this one was off by 0.059. This one was off by 0.001, right? If I plug 2 in here, 2 cubed is 8. And if I plug 2 in here, that'd be 24 minus 16, which is also 8. So this one is exact. And then going this direction, I'm going to go ahead and write them in. You can calculate those if you want. I already did. And 9.261, 9.2. So again, over here, I'm only off by 0.001. And here, I'm off by 0.061. So I get further and further, as I get further and further away with my x values, my y values are also changing more and more, right? I get further and further away from the truth, if that makes any sense. When I found this tangent line, I found it for x equals 2. I said, what happens when x equals 2? And that's how I wrote that equation. So it should be exact there, but it's going to be a little bit off as we go beyond there. Okay, so here's what differentials are, and you can read that definition. We have been working with differentials. I don't want you to think that you're doing something different. So let's talk about it in this problem right here. So this one says let y equal x, no, the square root of x. So that means y equals x to the 1/2. I'm going to rewrite that. They want me to find dy, okay? And they gave me some values, so I'm going to use those to my advantage. So when I do the derivative of this, I get dy dx equals 1/2 x to the negative 1/2 if I subtract 1, right? So we always write this derivative as dy dx. This is really the change in y over the change in x, or slope, right? So when they're asking me to find dy, they only want me to find that change in y. So I'm going to multiply by the change in x over here. Okay, so that's what's happening here. When they tell me that that's 0.1, I'm going to plug it in there, and then I'm going to move it. I'm actually going to move it first, and then I'll plug it in. All right, so let me simplify this because it's kind of messy. So dy dx equals, I'm going to rewrite this as 1/2 with my square root of x down there with it, because this is a negative, so that means it's in the denominator. So then I can rewrite this as, well, dy then is really 1/2 square root of x times dx. So this is really a differential. When they write it like this is what they mean. This is what differentials really mean. So then I'm going to plug in the values they gave me. They told me that x was 4 and that dx was 0.1. So I'm going to plug those in here. So dy is 1/2 times the square root of 4 times 0.1. And then I'm going to calculate that. So that means dy is really, this is really 2, so 2 times 2 is 4. So this is really 1/4 times 0.1, which ends up, it's really 0.25 times 0.1, which is 0.025. So I'm getting that as my answer for dy. Now, I found dy, that's what they wanted me to do, but then they wanted me to compare this value with the change in x. So that's where this error propagation comes in. So earlier when we found that table and we were like, the further and further we get away, the more we're off. That's what I'm finding here. How much off am I going to be? So this change in y, so I'm going to write it kind of backwards. The change in y equals my f of x plus change in x minus f of x. That's the formula that tells me what this is. Okay, so my change in y equals f of, I already know x and the change in x. So dx and delta x are the same thing. That's the change in x. So they told me that was 0.1. So this is 4 plus 0.1 minus f of x again is 4. So now I need to figure out, well, what is f of 4.1 and what is f of 4? That's what I'm really finding here. So f of 4.1, that was my equation right here. My f of x, or my y, equals the square root of x. So this is really the square root of 4.1. And this is the square root of 4. So f of 4, plug it in right there. So that's the square root of 4. So then I'm going to just solve this. So I end up with, I estimated this one to 0.025. Did I estimate that? Let me check that real quick. My brain isn't working. So yeah, I did. So that was 2.0248, blah, 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 blah. So I rounded that to 0.025, and then minus the square root of 4 is just 2. So that means my delta y is about 0.025, which is interesting. That means they are the same. So my change in y that I found is also my change in y that this equation found. So you could really use either method to find that if they were asking for it. So derivatives are pretty helpful, though. I feel like they're pretty easy to do. All right, example 3 says the measured length of one side of a wooden cube is 4 inches. So remember, on a cube, you've got length times width times height if you're talking about the volume of it. But on a cube, all of the sides are the same size. So I'm just going to call that S for side. And the volume of a cube, volume is S cubed. Side times side times side. All right, so they're giving me a lot of information in here. Let's kind of decompose this here. So the length of one side is 4. So that tells me that S equals 4. And then the measurement is correct to within 0.02 inches. So that means the measurement of the side length, so ds, could be plus or minus 0.02. So the change in that side length could be 0.02 over what I want or 0.02 under what I want, right? So it could be, it could be overestimated or underestimated. I hope that makes sense. So what I'm going to do is find my derivative. So the derivative of v is dv ds, because I'm doing this in terms of s, right? And then the derivative of s cubed is 3s squared. So then if I'm just looking for dv, which is what I'm doing when I'm doing differentials, I'm really just looking for that dv. That's 3s squared times ds. So now I'm going to plug in what I know. I know then that dv equals 3 times 4 squared, because s was 4. And ds was that plus or minus 0.02. Now, the good thing is if you forget this plus minus, it's not really going to matter that much, okay? So I don't want you to stress about that. Just know that this could be an over or an under estimation. Okay, so then dv, if I calculate that, I end up with a plus minus 0.96, okay? So here's what that tells me. The error propagated, making sure I'm spelling it right, error is 0.96, and we were talking about volume, so inches cubed, because this was in inches, right? So inches cubed. So what this means is I could have an overestimation of 0.96 or an underestimation of 0.96 if I'm calculating that volume, okay? Okay, so this section right here is telling me some, like, these are my formulas, sort of, but you guys know how to do derivatives, so I'm not going to go back through that. This is just a basic derivative, okay? So on a problem like this, if they want me to find dy, I'm going to do my derivative. So dy dx equals, this would be 12x to the third, and then minus 5 would be 0. And then I'm just going to pull dx over to the other side. So dy equals 12x to the third dx. That's all they're asking you to do there. So this one, this is a product rule. So dy dx equals, take the derivative of the first one, so that's 1, times leave that second one alone, so tangent of x I'm going to leave alone, plus x I'm going to leave alone, and I'm going to do the derivative of tangent, which is secant squared of x. And then I'm going to pull that dx over to the other side. So 1 tangent is the same thing as tangent, plus x secant squared of x. Now, when I do times dx, I'm going to put all of that stuff in parentheses because I'm taking that whole side times dx. If you put dx just on the end on the AP exam, they will count that wrong because it looks like it's only dx times this last piece. So make sure you do parentheses. When in doubt, do parentheses. Okay. The last one, that's a quotient rule, so I'm going to do it kind of off to the side here because I'll run out of room if I don't. So low times the derivative of the high is 2x, minus high times the derivative of the low is just 1, all over low squared. Now I'm going to simplify this, so dy dx equals, this would be 2x squared plus 2x minus x squared. Okay, so dy dx really equals at 2x squared minus x squared would be x squared plus 2x all over x plus 1 squared, but I'm taking all of that times dx because I went ahead and moved that over all at the same time while I was simplifying. And that's my final answer on that one. Okay, the last couple here I'm just going to fly through because we're just trying to give you as many examples as possible. This one, chain rule. Don't forget your chain rule. So dy dx equals the derivative of secant is secant tangent. And then that has to be taken times the derivative of the inside. This right here is the inside part. So I left that exactly the same here. Now I'm going to do the derivative of this, which is 6x. So, and then I'm going to move my dx over. So I'm going to put the 6x up front, and then I've got a secant of 3x squared and a tangent of 3x squared, and I'm going to take all that times dx. Last one. Again, we've got a chain rule. So I've got dy dx equals, bring your -1 down front, leave this exactly as it is, subtract 1 from your exponent, and then times the derivative of the inside would be 6x squared. Then I'm going to simplify this. So let's see, I'm going to write it as a negative up front. A 6x squared is fine to stay on top, but all of this has to move to the bottom. And then I need to move my dx over. So dy equals negative 6x squared over 2x cubed minus 7 squared, all of that times dx. And that's it for this lesson. It's not too bad, just a good review and a good reminder of how to do your derivatives.